In this video, we're going to talk about 7.4.2, which is called transforms of integrals, but they're convolutions is another name for them. And the convolution theorem is going to say that the Laplace transform of the function f, and then we use the special operator star of g, like that, is equal to f of s times g of s. Likewise, if we are going to have the inverse Laplace transform of f of s times g of s, then that's going to be equal to f star g. That's all that I'm concerned about in this section. If your teacher wants you to do more than that with the definitions and things like that, then they can show you that in the notes. And so I'm not going to follow the textbook instructions exactly, but these are going to be based off of the textbook problems, starting with number 19. And we have an f of t given to us as 4t, and I have a g of t given to me as 3t squared. So my capital F of s is equal to 4 over s squared. My capital G of s is equal to 6 over s cubed. So my G is 24 over s to the fifth. I'm going to do number 20. There's very few examples of this, so I'm doing the evens and odds with you. But again, the instructions are a little different because they tell you to not just jump in and use the theorem that I'm using right away. They tell you to use the definition. And I don't find that necessary at this point in the class because you've already done Laplace transform definitions. So go ahead and do them if you want that way. And so my Laplace transform of f star g is going to be 1 over s squared times s plus 1. Moving on now to number 21. This is f of t is equal to e to the negative t. G of t is equal to e to the t. So my f of s is 1 over s plus 1. My g of s is 1 over s minus 1, making my Laplace transform of f convolution g is 1 over s plus 1 times 1 over s minus 1, which is equal to 1 over s squared minus 1. 22. F of t is equal to cosine of 2t. G of t is equal to e to t. And that makes f of s equal to s over s squared plus 4. Capital G of s is equal to 1 over s minus 1. So Laplace of f convolution g is equal to s over s squared plus 4 times s minus 1. 23 asks us to find Laplace transform of one convolution t cubed is going to be 1 over s times 3 factorial over s to the fourth is going to be 6 over s to the fifth. 24 is Laplace transform of t squared convolution t e to the t, which is going to be 2 over s cubed times 1 over quantity s minus 1 squared is going to be 2 over s cubed times s minus 1 quantity squared. 25, Laplace transform of e to the negative t convolution e to the t cosine of t is equal to 1 over s plus 1 times s minus 1 over s minus 1 squared plus 1. It's going to be equal to s minus 1 over s plus 1 bracket s minus 1 squared plus 1. Don't need to simplify that. That's fine to leave it just like that. Let's look now at number 26. We have Laplace transform of e to the 2t convolution e to the t cosine of t. And that's going to be 1 over s minus 2 times 1, this is sine t. 1 over s squared plus 1. And that makes this 1 over s minus 2 times s squared plus 1. Let's go the other way and do an inverse Laplace transform now. Skip down to 35. Inverse Laplace transform of 1 over s times s minus 1. It's going to be Laplace transform of 1 over s times 1 over s minus 1. It's going to be 1 convolution e to the t. 36 is inverse Laplace transform of 1 over s squared s minus 1. Is equal to inverse Laplace transform of 1 over s squared times 1 over s minus 1. So that is going to be equal to t convolution e to the t. And your answers in the textbook are going to go further because they'll solve that convolution out and give you an answer that's further along in the process. This is just as far as I personally care about. Let's go ahead and keep going here though. 37. inverse Laplace transform of 1 over s squared times s minus 1 is equal to inverse Laplace transform of 1 over s squared times 1 over s minus 1. And so, sorry, that's a cubed there, cubed, s cubed. And so this is going to need to be inverse Laplace transform of, I need a 2 up here for my 2 factorial for s cubed, and I need a 1/2 out there to balance it, 1 over s minus 1. So this is 1/2 of the convolution of t squared and e to the t. And 38 is inverse Laplace transform of 1 over s times s minus a quantity squared is inverse Laplace transform of 1 over s times 1 over s minus a squared. And so that's going to be 1 convolution t e to the at. That's it for that section for me. I'm not going to do 7.4.3 with transformations of a periodic function. So again, if you do those in class, great. But typically, this is kind of it for chapter 7 with the depth that I'm used to. So if your teacher goes deeper, excellent. I'm going to go on and go back to cover that section from 2.6, which coincides with the beginning of chapter 9. And that will I'll do those together, one video that covers the same topic that's in 2 different sections of the textbook, and that will be the last video that we're going to do. It is a numerical estimation technique similar to how you had the trapezoidal rule and Simpson's rule for integration and things like that. It's this kind of, it's that same kind of idea of how you could find approximate solutions to differential equations and things like that using a method that we're going to cover there called Euler's method. So there's other methods that are also covered in the book. We don't really use Picard's method anymore, but you can look at that. So anyways, we'll come back next time and talk about a problem or two with Euler's method. It's quite a lengthy process, so I'm probably going to do only 1 or 2 examples at most. Have your graphing calculator ready to help you, because you'll want to use the table feature in there with that video just to help you do some of the calculations. All right. Have a great day. See you for the next and last video of this series before we do the bonus content later for chapter 8 at a later date and time.